We'll start here and pick up where we were in the last video. So we want y sub 1, which is the last or initial y value, which is 0, plus the slope through the previous point, that's 1 over the x coordinate, right? This is dy dx through the previous point is 1 over 1 times a change in x. So that's 1 times 0.1. So that's just 0.1. Now, I do want to make a point here. We're going to do something at every step along the way when we're taking multiple steps. We're going to stop at the very end, and we're going to write down the coordinates of this point, the x coordinate as well as the y coordinate. So if we started at x equal 1 and we added 1 step size, now our new x coordinate is 1.1, and we found our y coordinate to be 0.1. So I want to make sure that you're doing this step at every step along the way, because this is what gets plugged into your differential equation here at every step during Euler's method. So y sub 2 is the previous y output, which is now y sub 1, plus the slope, the differential equation, through the previous point. And here is why doing that step is so important. And again, times a change in x. So specifically for this problem, y sub 2 is y sub 1 plus the slope through the previous point, the slope is just 1 over the x coordinate, times 1 step. Now, this is obviously a calculator question, so I've got my calculator here, 1 divided by 1.1. I'm multiplying that by 0.1, okay, and I got 0.0909, and I'm going to add that to 0.1, and there is y sub 2, and I find that y sub 2 is 0.190909. All right, so that's what I found y sub 2 to be. Now again, I'm going to go back and I'm going to find x2, y2, because I'm going to have to plug that in to take my next step. So I was at 1.1. I took 1 additional step, which is another 0.1 horizontally. So now my x coordinate is 1.2. My y coordinate is 0.191, or however long you want to draw that out. Notice that I actually wrote many more decimal places than I need. And that's because I want to make a point here. I am carrying this value forward into my next step. If I just stopped at 3 decimal places, then when I take that approximation and add to it another approximation, then my result on step 3 will no longer be accurate to 3 decimal places. So when you're using decimal approximations in the middle of your work, something that's multi-step, please remember to carry more decimal places with you. Now your answer has to only be accurate to 3 decimal places, but again, you want to make sure that every subsequent answer is accurate to 3 decimal places. So remember that, and Euler's method is a place where it shows up often. All right, so y sub 3 is the previous y output, now we're at y sub 2, plus the slope or differential equation that you're given through the previous point, now we're at x2, y2, times a change in x. Now, you don't, when you're answering these questions, you don't have to show this step. I'm doing this for teaching purposes. Your work would involve this step, and then this final step. So y sub 2, and this is where I'm going to pull down more than 3 decimal places, plus the slope through the previous point, now we're at an x value of 1.2, times a step size. And now this is actually going to be the answer that they're asking for. So 1 divided by 1.2 times 0.1 plus 0.190909, and I get that is approximately 0.27424 if I entered all that correctly. So my actual answer, what they actually asked for, was the approximation to the output of the function in 3 steps with a step size of 0.1. That's where I am. No, here's where I am. See why that step's so important? X sub 3 is 1.3, thank you very much. And so y sub 3, or the output of the function, is approximately 0.274. All right, we have one more example we're going to work through here. It's kind of calculator intensive. And as a matter of fact, I really don't think it's necessary that we do all of these steps. So I may just do the first 3 steps, and then you can do the last 2 steps on your own if you want to. But the process is the same. Use Euler's method with a step size of h equals 0.1. Why is it h? It's not h on the test. I've never seen them use h on the AP test, but if you look in your textbook and any other calculus textbook, h is used a lot to represent the step size in Euler's method. So I just wanted to stress that here. To find approximate values of the solution at, and this is, I cut and paste this off the internet, and I should know better because this should be x equal 0.1, 0.2, 0.3, 0.4, and 0.5. So it's asking for f of 0.1. We need to use Euler's method to find that approximation. F of 0.2 and f of 0.3, and so on. So this is how we need to, give them our answers at every step along the way. So I'm just going to take off and do Euler's method without writing the formula down. I'll write the formula for the first one up here, but I think you understand what I'm doing with it by now. But again, you need to have this in between your ears. This is something you need to immediately be able to pull up when you read Euler's method and go with. So our initial point is the point 1, 0. So x naught is 1, y naught is 0. So we need the last y output plus the slope through the previous point, 2 minus e to the negative 4 times 1 minus 2 times 0 times a step size, and they told us the step size was 1. So you can clearly see why we're going to have to use a calculator for this. And I tell you what I did. I put this part of the differential equation, just because I'm lazy or smart, I'm not sure which, I put that into y1. I have 2 minus e to the negative 4x in y1, so I can at least evaluate that part of my slope using my calculator, because then I just pull up y1 using my vars button, and here x is 1, so I'm just going to plug a 1 in there. I got 1.9816. I would normally then go ahead and subtract 2 times whatever the y-coordinate is, but here the y-coordinate is 0, so this actually is the slope through the initial point. I'm going to multiply that times a step size, 0.19816, and then I would add that to the initial y value. Well, here it's 0, so I have 0.198168. And notice I have given myself more than 3 decimal places. I would only show 3 decimal places accuracy in my answer, however. Again, we're going to stop right here and we're going to find x1, y1. If we started at x equal 1 and we took a step size of 0.1, then x1 is 1.1 and we found y1 to be 0.198168. So now the next step, and again you can see why I'm not going to do more than probably about 3 steps because it's just too time consuming. But I need the previous y output, and this is where I would definitely write more than 3 decimal places, because if I only put 3 decimal places down here and I add, something really crazy and decimal intensive to it, then that result will no longer be accurate to 3 decimal places. So make sure you carry more decimal places. So this is 2 minus e to the negative 4 times 1.1 minus 2 times 0.198168. Even here I'm carrying more decimal places, times 0.1. And so let's see, I'm going to go back and pull up what I have in y1. I'm evaluating that in an x value of 1.1. I'm now subtracting from that 2 times 0.198168, and then I'm multiplying that by 0.1. I'm plugging all this in my calculator as I'm talking to you. And then I'm adding 0.198168. So really calculator intensive work here. So if I plugged all that in correctly while I was talking, and it wouldn't surprise me if I didn't, but I get 0.357306666666. I'm going to take the time to find x2, y2, and so I started at 1.1. I took a step size of 0.1, so now I'm at 1.2, and I'm at 0.357306. I would only give my answer accurate to 3 decimal places, however, but I'm going to carry more than that forward with me. So I'm just going to take one more step here. I think you get the general idea. It is the previous y output carried to more than 3 decimal places plus the slope through the previous point minus 2 times 0.357306 times a step size. So we'll see what we get there. I'm going to pull up what I have in y1 again and evaluate it at x equal 1.2. I'm going to subtract from it 2 times 0.357306. Take that result, multiply by 0.1. Take that result and add 0.357306. And again, while I was talking, if I did all that correctly, 0.485021, accurate to 3 decimal places. I would show them that I understand that's 0.485. So I'm not going to waste your time or mine by doing the last 2 here. We can just mark those out. But you get the general idea. And this is what your work would look like on an Euler's method problem. So make sure when you come in tomorrow to do homework, or whenever the next class period is, when you come in to do homework, make sure this is in between your ears, because this is what you're going to be using answering Euler's method problems. Okay, so that finishes this lesson. Come in next time and we'll work some homework.